Hello, in this video we're going to look at probability distribution and expected value. So a probability distribution essentially tells us that we have several different characteristics that we'll have. So one of the first ones is that when we're dealing with the probability of a random variable, that probability of that random variable must be between 0 and 1 inclusive. So if we have that any of the probabilities are negative or greater than 1, then we say that it cannot represent a probability distribution. Now that's kind of strange given that, you always hear those terms like 110% or 150%. Well, in terms of like a specific experiment, we say that that just doesn't happen. So the other characteristic that we can look at for probability distribution is that the sum, so we'll just write it like this, the sum of all of the probabilities must equal to 1. So if we have that a probability distribution table was given, and it did not add up to 1, then it does not represent a probability distribution. So for example, let's say that we had a probability distribution of where we had our random variables are 0, 1, and 2. Well, let's say that this is going to be 0.25, and this is going to be 0.5, and this was 0.25. Then this definitely does represent a probability distribution, specifically because I have that if I was to add up the probability of 0 plus the probability of 1 plus the probability of 2, this would in fact equal to 1. And we can check that by saying, well, you have 0.25 plus 0.25 plus, well, I was supposed to write it last, but okay. Actually, let me go ahead and erase that because that'll get confusing if we say that that's the probability of 1. So that's going to be a half plus 0.25, and yes, this does equal to 1. So it does represent a probability distribution. Now, let's say that, for example, that we don't have a probability distribution table, but we know the specific experiment that's being conducted. So, for example, let's say that a coin is tossed, let's say 3 times. And the number, so we'll just say the number of heads is counted. So we just want there to be the number of heads that's going to be counted. So what that means is that we would need to figure out like what is the random variables. Okay, so let's say that we want to find the table as it applies to a probability distribution that's binomial. So, well, it doesn't necessarily have to be binomial because you can still construct the table even if it was using counting techniques, but for simplicity we'll just stick to binomials for this example. So we have that it's tossed 3 times and the number of heads is counted, so that means that our possibilities are 0, 1, 2, and 3. So that means that we're going to need to find the probability that x is 0, 1, 2, and 3 respectively. So the other thing that we'll need to add in is that the probability that it lands on heads is a half. So we got that much. So let's go ahead and find the probability that x is equal to 0 is binomial PDF 3, 1/2, and 0. Now, if we go ahead and we do that in the calculator, that's going to be second vars binomial PDF. Trials is 3, 0.5 is our p, and our x value is 0. So that's going to give us 0.125. So this is going to be 0.125. The next one is to figure out what is the probability of 1. So the probability of 1 is equal to the binomial PDF 3, 1/2. Now, if we do that, we're going to just go ahead and just replace the 0 with 1. So we have that that's going to be 1. Now, because I have this available, let's go ahead and just say that we'll do the next one, which is 2. And then we'll just click enter. So notice that these both are the same. So we'll go ahead and do one more computation. That'll be for the 3. Now, interestingly enough, we'll see that the third one is the exact same as the first one, and that's no coincidence. So we have that that's going to be, we said 0.3, was it 75? Yep, 75. Okay, and then we found out that the probability that x equals to 2 was also 0.375 using the calculator, and then we figured out that the probability that x equals to 3 is 0.125. Okay, so what that means is that we can actually just go ahead and make our table. So our table is x, and then we have p of x is 0, 1, 2, and 3. So we have 0.125, 0.375, 0.375, and that should be 0.125. So we have 125, and that's it. So this gives us the probability distribution table for if we were conducting a coin experiment. Now, my next topic is looking at what we call the expected value. Now, the expected value is given by basically just taking the sum of our random variable x and multiplying by p of x. Now, expected value is more or less just like a form of an average. So, for example, if we look at our initial probability distribution table, we have that this was 0, 1, and 2. So let me just draw that that probability distribution table again. So we have 0, 1, and 2. But the probability distribution table said 0.25, 0.5, and 0.25. So that means that the probability, or let's say the sum of x times p of x, that's going to be equal to 0 times 0.25 plus 1 times 0.5 plus 2 times 0.25. So what this does is it gives us 0 plus 0.5 plus 0.5. So interestingly enough, if we just add this up, we get 1. So the expected value is 1. Now, what if we had that we were going to look at, for example, um, a family. So suppose that there's a family of 4. And let's say that the number of girls are counted. So a typical question might ask, like, find the expected number of girls. So if we use the expected number of girls in the family, well, we have to basically construct the probability distribution table. But let's go ahead and think about it like this. We know that that basically you have that in an experiment like this, you have that either the child is a boy or the child is a girl. That's assuming no multiple births. So what this means is that there's a total of 2 to the 4 possibilities. So that means 16 possibilities. The next step is that we can basically just go ahead and figure out, well, what is my random variable? My random variable is that it's going to be the number of girls that are in the family. So the possibility is that they have no girls. So that's going to be all boys. So that's 0. Then you have 1 girl, 2 girls, 3 girls, and then 4 girls. So that means that we can actually compute the probability of each of these, because we know that all that we need to do is just find the number of ways that we can select no girls, 1 girl, 2 boys, 3 boys, and 4 girls. If I said boys on accident, I apologize. Let's do it like this. So the way of which that we can kind of look at this is that, well, to find the probability of 0, and you can use the binomial distribution if you want to, but we really don't have to. So this is going to be 16, but think about it like this. If there's a total of all boys, that means that there's only just one way that that can happen. So that's 1 out of 16. But if we look at the probability of 1 girl, well, the probability that there's 1 girl is basically just going to be 4 out of 16. Why? Because we're thinking about it like we have a boy, a boy, a boy, and a girl, meaning that there's 4 different ways that this can happen, because you just move the girl from last to second to last to the second to the first, so that's going to be 4. Now similarly, if we use the probability of 2, well, that means that you have that there are 2 girls and 2 boys. So that's going to be, if we kind of just go about moving this around, that's actually going to be a little difficult. But if we just use the combination formula, that will work the same. So combination for choose 2 out of 16, that's going to be, that should be, for choose 2, it's going to be 6. Yeah, that's going to be 6. So that's going to be 6 out of 16. Now if we go ahead and calculate the probability of 3, Well, that's going to be very similar to the probability of 1, because in this case you have that there's going to be 3 girls and then 1 boy, so that's going to be 4 different possibilities out of 16, so that's going to be 416. Now, the last probability is the probability of 4 girls, so that's just going to be 1 out of 16. So that means that we have our probability. Now, I would advise that you would just go ahead and construct the table in whichever manner that you feel most comfortable doing, because in either case, you have to know how to construct the table using any methods. So our probability distribution table is as follows. We have 0, we have 1, we have 2, we have 3, and then we have 4. I'm just going to write these as fractions just because it's more convenient. So we have 116, 416, 616, 416, and then 1 out of 16. And notice that if we add all of this up, it does equal to 1, which is no surprise. So next we just need to find the expected value. So the expected value is the sum of x times p of x, which this is going to be 0 times a 16th plus 1 times 4/16 plus 2 times 6/16 plus 3 times 4/16 and then let's go ahead and just move this slightly. Okay, so we'll just do plus 4 out of 16. Now when we add this up, this is going to be 4 plus 12 plus 12 plus 4, all divided by 16. Now this is going to be 32 out of 16, but that's just equal to 2. Okay, so what that means is that we figured out that the expected number of girls in the family is just 2. So they should expect that, if they're going to have that many children, that they would expect that half of them would have to be would be possibly a girl. Now that's actually one way to do it, but another way that you can possibly do this is by saying that for any binomial, the expected value is n times p. Well, that actually makes kind of some sense, because if you have it's binomial, then that means that you're just going to multiply the total number of trials times the fixed probability. So like, for example, we knew that the number of children in the family was 4. The fixed probability was 1/2. But if you multiply the n times the p, you get 4 times 1/2, which is actually just equal to 2. Okay, so that took like no time at all. So that means that if something is binomial and you're looking for the expected value, that means that it's just n times p. So for that matter, we know that for a coin, the expected value is going to be just like, it's going to be the n times 1/2, or just n over 2. And then for the die, it's going to be n times a 6th, or just n over 6. I only put it like that just so that you kind of get an idea. Like if I knew what n was, then I just go ahead and plug it in. And the same thing would be for like, if it was a true or false question. then it's essentially the same exact thing. It's going to be just n over 2. But it's best to like just look at, a particular example where you're given the number n and then you're given the probability of p. So, like if you have that there's like a 50 question quiz, that the possibility, and let's say that you have that it's true or false, then in that case you know that you're just going to take the 50 and you're just going to multiply by 1/2, because you have that there's only one answer choice that's correct. So that means that you would expect to get 25 of the questions correct. And that's kind of like, if you think about it as that you're just purely guessing what those are. Now, be sure that you do look at some of the questions where it involves a little bit of probability techniques with counting, because when you're constructing the probability distribution table, you may need to use those techniques to construct it, which means that the formula for the binomial won't necessarily work, because it's only easier when it's a binomial. So with that, try to see if you can do kind of like this example where I constructed the probability distribution table for the family that had 4 children. Okay, please let me know if you have any questions. This actually completes the material for this semester. I'm going to post a few more videos though, just for the sake of completing the course.